Okay. Hi, everyone. Welcome to the International Methods Colloquium. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. I'm Jess Nessery, Associate Professor of Politics at Wake Forest. This week's speaker is Luke Keele, professor of the McCourt School of Public Policy at Georgetown University and currently teaching at the University of Pennsylvania. His talk is entitled A Review of Geographic Regression Discontinuity Designs, which, as you can see, is joint work with Rocio Titunik. Luke's talk will last about 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Q&A button that appears at the bottom of your Zoom webinar window. And I want to say you can ask questions at any point in the talk. We will get them and I'll see them. But unless they're clarifying, we'll hold all the questions to the end of the talk and give Luke his uninterrupted time. A link to the slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation. And I will post that link just as soon as we get started. And with that, I'd like to welcome Luke. Luke, welcome.
Hello, everyone. Hello there. Excited to proceed. This is haven't worked on this in a little while, but it was a big project where we started with an application and it led to many, many methods papers. I often think that the best methods work is where you start with a problem and then you spend a lot of time figuring out how to solve it. So let's get started. I think it probably for most people know that these days, in terms of the causal inference literature, regression discontinuity designs are sort of the hottest thing going. In general, if people say you should do a natural experiment, they would prefer that you did regression discontinuity design. And I think that summarized this quote. This is a quote from a review of RD designs. I think that sort of summarized that. And it says another reason for the recent wave of research is the belief that the RD design is not just another evaluation strategy, and that causal inferences from RD designs are potentially more credible than those from typical natural experiment strategies, i.e. difference of differences or instrumental variables, which have been heavily employed in applied research in recent decades. So what is it that makes the RD design so attractive and so popular? I would say there's two main things. One that makes it work is that it's a known treatment assignment rule. That is, right, in an RD design, there is a continuous score. There is some value at which people above that score are treated and below that score they're not treated, right? Similar to randomization, that is a treatment assignment rule that someone has to impose on the world, right? Someone has to actually go out, and in the classic example with like PSAT scores, someone has to set up that rule and enforce it. And there's actually, you can show that there's aspects of RD designs, they tend to fail when the design is not appropriately delivered. So given that, moreover, then on top of that, there are a set of falsifiable assumptions. That is, there's a set of falsification tests that allow you to way to sort of check whether it appears to be a good regression discontinuity design or not. So one thing that occurred to us, Rocio and I, when we first started talking about this topic, about 9 years ago, is that it's often quite clear, right, that laws and regulations often change at geographic limits, right? It could be the case that, particularly in the US case, but in other cases, but particularly in federal systems, right, there's always subunits of government and they pick different laws, and right, the people who, that is, the people who are at the border between a city and a county, or state or country, right, they face different laws. So one example that we looked at is media markets and the effect on turnout. That is, in the United States, people are in one media market and versus another. And if you're in a battleground media market, you get lots of presidential ads. If you're not in the media market, you get very few presidential ads. And right, there's literally just lines where the media market changes. And you can show the amount of ad volume that people get is dramatically different depending on what side of the media market boundary they live on. We looked at ballot initiatives. Some people may be in an area with a ballot initiative versus an area that doesn't have a ballot initiative. The entire literature on a large part of the literature on voter turnout is focused on voting regulations. Voter ID is sort of the most commonly talked to one about those, but right, those are all different. All those voting regulations are all mapped typically in the US in particular to subunits where the treatment changes discontinuously at the border of the unit. Another example, there's many examples in economics, but one I've seen is mortgage laws. That is, do you live in a state with different mortgage laws and how that affect whether you had to go into foreclosure or not during the financial crisis, right? So the one question is can we treat these borders as just generalized regression discontinuity designs? And if so, are there any sort of special characteristics of these designs that we need to take into account? And today, that's mostly what I'm going to focus on, is sort of the particularities that arise when you're using geography as a regression discontinuity. So I'm going to use a motivating example throughout. This is technically from health services research, but it's a very social sciencey thing that should be easily understandable by any sort of social scientist. So in the US, there is a program called the Children's Health Insurance Program. Like many health programs, it is federally funded. That is, the federal government gives money to states, and then the states administer it and set lots of different rules about how the program is run within that state. So in February 2008, the state of Wisconsin decided to add co-pays to CHIP. That is, people who had CHIP insurance, when they went to the doctor, had to pay a certain set of co-pays. Before, there were no co-pays. So to just give you a little bit of an idea, right before the February 2008, if you had CHIP, you could just use any of these health services as much as necessary. But now, right, it would be $3. They're fairly minimal amounts, but it was $3 for an emergency if you go to the ER, $3 for hospitalizations, and you can see the only thing that was not left off is preventative care, well child visits. They didn't add any copay for that, right? And this is your classic example. So the states here, or this is kind of hard to tell, but the green counties, those are Illinois counties, right? Those are control counties we may think of. That is, Illinois didn't add any copays. It also has a CHIP program, but it had no copays to it. The purplish bluish counties, right? Those are counties in the state of Wisconsin, right? As of February 2008, they are now treated in that they are now copays on the use of health insurance. And one question might be is if you add copays, does that reduce the amount of utilization of medical services? Right, and in particular, one thing that's very fascinating about these designs is if you spend some time looking along this border. In fact, if you go to this little area here, most of this is actually rather empty. But if you go to this area here, there is a town by the name of Beloit, right? And this is the Wisconsin side, and this is the Illinois side, and it's literally split right through the middle, such that the people who are in CHIP on this side now have copays, and people who live in CHIP utilize CHIP on this side no longer have copays, right? And you can start to see very much the flavor of why this might feel like an RD, where we might think, right, that the people who are close to the border, right, should be fairly similar to these people, thus such that, right, the idea being here is a good as-if counterfactual for the people who live on this side of the border. Right. So to walk you through how these designs work, I want to do a little bit of a review on a particular type of regression discontinuity design. In the classic regression discontinuity design, there is a single score or running variable that is like your PSAT score, right? There's only one of those, and if you're above a cutoff, you get treated or not. In political science, the big one is vote share. There can be different cutoffs, but typically there's just a single vote share. There are RD designs, however, where there are quote unquote two scores. The classic example here is you can imagine two tests that you have to take, where on each one, let's say one is language arts and one is mathematics, and you have to get above a 50 out of 100 on each test before you graduate. There are actually about 12 or 13 states that roughly operate on this principle, where they have test taking at the end of high school, and you have to pass these tests to graduate, right? So, right, imagine there that you have to take these two tests and you get a 50 on both, you graduate, right? And you can quite easily map, right, create a little XY diagram here where this is your math score and here's your language arts score, right? And clearly here, we could think of this in terms of regression discontinuity design, right? The idea is to compare people, right? Anyone in this area is treated. The idea, of course, being that the people up in this corner who get, say, perfect scores on both tests are not particularly good counterfactual for someone down here who scores poorly on both tests. The idea being, of course, is that people who are near this border who just barely pass both tests may be good counterfactual people for both people who just barely fail both tests, right? And in mathematics terms, right, well, essentially what we're saying is we now need continuity, right? The classic RD design assumes that everything is except treatment assignment rule is not changing at a particular cutoff, Well, here, right, ideally the way I think it's easier to just sort of visualize this is now we're looking at this as a three-dimensional space. The idea being here, you can see in here the treated region is this little area here. The idea being is that if you're just inside this border, treatment assignment changes continuously, right? If you're 51, 51, you graduate. If you're 49, 49, you don't. The idea being is that background characteristics, while they're quite different up here at the perfect scores versus people who fail both tests, right? The idea being that those are changing very smoothly, such that if you're right near that border, those characteristics are almost identical if you're just above or just below the border, right? That's the general idea of a regression discontinuity design translated into a setting in which there are two scores, in this case, two test scores. So the only thing that changes now is, right, we have two scores, and we now have a treated region instead of just being above a treated cutoff. And then our this idea behind identification, that is the potential outcomes, the idea of continuity has to now be a plane instead of just a single line. So let's think about how that's going to relate to geographically discontinuous treatment assignments, right? So formally what we're saying here is we have a treatment assignment that changes discontinuously along a border, right? We have a treated area and we have a control area. In the example I've been talking about so far, right? Illinois is the control area and Wisconsin is the treated area. As soon as you cross the state border, you have copays, right? The idea here is that while perhaps Wisconsin and Illinois are somewhat similar, it's easy to think of ways in which they're different, right? Milwaukee is the largest city, but Chicago is a much larger city. We might imagine there's a much larger minority population. SES may be lower, right? There are all different ways that we can think of that Wisconsin might differ from Illinois. The idea here being, of course, is that we think that people who tend to live just on one side or the other may be good counterfactuals for each other, right? That is, it might be a suspect to compare Wisconsin to Illinois. It may be much less suspect to compare people who just happen to live perhaps in one state versus the other. Again, thinking back to the Beloit side, right? The Beloit example, it's quite intuitive, right? If you imagine, right, that the state border just happens to cut this town not quite in half, but in say thirds, and that the people who live near that border, right, it's essentially as if random that they ended up there. Right, so in this notation, right, we have to define a two-dimensional score here. And now this two-dimensional score, this is just generic notation, but this first score is going to essentially be a geographic coordinate system, the most obvious one being latitude and longitude. When I got into this, I found out there are a couple others. But we imagine this is going to be latitude and this is going to be longitude, right? And we're going to define a set that collects the boundary points. That is, what values of latitude and longitude form the border between treated and control, right? And you can imagine, right, along that border, right, you can pick out any point of latitude and longitude that's at that border, right? And the way treatment assignment rule operates here, right, is that you are treated, if you were in treated area 1, right, for any set of latitude, points of latitude and longitude that are within Wisconsin, and your control for any set of latitude and longitude, right, that's strictly speaking inside Illinois. So in one of the papers, we go through slightly more mathematical argument, but you can show, right, that there is mathematically anyway, absolutely no difference between the Wisconsin-Illinois example and the little toy example I showed you about the high school graduation test, right? That is, your score on the language arts and the math test essentially form a coordinate system. You can plot those coordinates, right? And if those coordinates then form an area, and there is a treated area and a control area. Latitude and longitude function in the exact same way. That is, right, it's different here in the sense that, and we're going to come back to this later, it's going to be important. What's different here is you're sort of already in an area typically, and then the treatment happens to you when you happen to be in that area, right? And here, right, latitude and longitude form the treated and the control areas, right? So mathematically, there's actually complete equivalence between sort of having two test scores or any sort of two-dimensional RD and then assigning treatments in terms of geographic areas. Right. So here, as I said, the coordinate systems are equivalent to each other. So that said, what might we be interested in terms of estimating? What's the causal estimand? Here, and this is true for both the geographic design and the more standard RD design, is right, this is the average counterfactual difference. This is going to be, in this case, the average difference in healthcare utilization. But you can now define that at a specific point. right? You can define there's a treatment effect for that whole border, right? In theory, there could be a big treatment effect in one part of the Wisconsin border and no treatment effect in another. So you can now define the treatment effects at any point you care to define, right, across the line. Strictly speaking, right, the treatment effect here is actually a plane that varies. Alternatively, what's probably a little more common is you can simply average across those boundary points, right? And that's going to give you the average effect across the border. That is here, what we're talking about is you can define the treatment effect, right? Which would be the density, right? The difference between people who live here and the people who live here for a given degree of latitude and longitude at this point. Or instead, right, you can average across, you can take those depending on how many points of latitude and longitude you've selected. You can just average across that and get an average effect right here in some sense across the entire state. Right? That would give you the average effect for people who live at the boundary. First, we played around with some different types of methods for estimation here, but you can show that pretty much standard RD estimation methods can be applied with fairly minor modifications. There was an earlier IMC by Rocio who has done a lot of work on sort of RD estimation methods, and much of what she talked about can be applied to these designs without any particular, with very little modification. So in the end, right, given what I've summarized so far, it would seem that, right, okay, we've got an RD design, geographic RDs are just two-dimensional RD, no big deal. Well, mathematically, they are the same. It has been in our experience that there are actually a number of differences. So the first one is that often the case that true geographic coordinate information may be missing. That is, the actual score here is latitude and longitude for each person. In this case, you could think of a household. That is, you need the actual coordinate system for each of the actual units in your study. So for example, in the data set we have, for privacy reasons, you're not given addresses, you can only get the zip codes. So oftentimes, right, we only have the geographic location of some coarser unit, right? Zip codes, you might have the centroid of the zip code instead of the location of where someone actually lives, right? Now what that does, it has now made the running variable, right? As soon as you move from not having latitude and longitude to each unit to any kind of aggregate geographic unit, the running variable is now discrete. It's not so widely known, but running variables with discretes have their own whole set of particularities and estimation methods that differ from classic RDs that have continuous scores. I'm not going to go into what those are because Rocio actually has a very nice textbook that she's working on that covers these in detail. But it's often the case that just the nature is often in terms of social science data, it's becoming more prevalent, but it can often be difficult to have precise geolocation for all your units, while aggregate geographic units tend to be pretty common. The other thing that tends to happen is your border often contains multiple possible treatments. Let me explain what I mean by that, right? So strictly speaking, what has changed here is the eligibility rule for medical copays. However, right, if you go through and look, the CHIP program, right, also that Wisconsin administers also differs from Illinois in a number of different ways. In fact, right, we can think of lots of other things that change at this border. The tax rates, Illinois has slightly higher taxes, though they're not so different than Wisconsin. But there are lots of other things that actually can change at the border, right? That is, contrast that to this test score example, right? That is here, classically, it's hard to imagine anything else has really changed except the fact that you've got different test scores. What we have to then assume is that these treatments are either separable, that you can estimate them out, that they're separable, or instead that you care about the compound treatment effect, right? Strictly speaking, this example, we can't estimate the effect of the actual medical copays. The only thing we can actually estimate is the effect of being in Wisconsin versus being in Illinois. That is, we can't rule out that there are a number of other things that may have changed at that border. All right. CHIP is a standalone program, so it's maybe slightly less problematic. But let's go back to the media market example. This is one of the ones we did where there's a media market example, and you're looking at whether someone who lives in a battleground media market who sees lots of ads, are they more likely to vote than someone who lives in a non-media market where they see no presidential ads? The issue there, right, is that the media markets actually almost entirely in the United States track county borders. In many states, counties are in charge of election administration. So in that case, you may be trying to estimate the media market effect, but let's say that one of the treated county is actually much stingier in terms of polling places, and people have to stand in longer lines, or thus less likely to vote, right? Given there's now a compound treatment, you can't separate the media market effect from the county administration effect, right? That is something we've seen happens a lot. The other big issue is oftentimes your county border might track a school district border. So there you can't estimate the difference, separate the difference from the school district from any other aspect. So the other thing that happens is RD designs are, as I said, one of their strengths is that they should validate, so to speak. That is, as a set of falsification tests. That is, one thing that's standard advice to do is to take pre-treatment covariates and then run the RD model, so to speak, on all those covariates, and you shouldn't find any difference, right? That is, if people are truly similar just above and below, you should find, right, that their characteristics are essentially the same just above and below this kind of. What we have found with alarming regularity is that it is the case that if you compare people, if you look at baseline covariates and you see how they change as you get closer to, say, a state or city border, they too tend to get more similar. However, what tends to be the case is it's not there. When you get right down to that border, the effects are not zero. So to give you an example, so this is an example where we looked at a ballot initiative in Milwaukee versus people in the Milwaukee suburbs. So they have ballot initiatives in Milwaukee, they don't in the suburbs. The idea is that people who live along the city border between Milwaukee and the suburbs should be similar. So one thing we like to do in these settings is look at house price, right? House prices tell you a lot about an area. So here, if you look at the countywide comparison, that is, houses in Milwaukee are substantially cheaper than houses in the suburbs. They're about $64,000 cheaper. And here we're just using, right, 1,000 meters from the buffer, from the state. So a buffer means we're taking everyone who's 1,000 meters from the city limit. So you can see that if you get out to there, it's dropped. It's still fairly substantial. And if you get closer and closer, here we're talking about people who live within 50 meters of either side of the border. We're still at $12,000 difference. That is, homes are still $12,000 cheaper in Milwaukee. So this is, as I said, right, something's going on. Geography is clearly making people more similar, but there's still some clear difference between people who they're right at that border. Right. Moreover, the other thing that can happen if you're using coarse units, like let's say you're aggregating up to city blocks, let's say you only have census data at the city block, or maybe even a bigger census region. The issue there is when you aggregate, so that if you do any work in spatial stuff for geographic analysis, there's something called the modifiable area unit problem. What that refers to is if you have something that varies in space, let's say income varies in space spatially, if you aggregate that up to an arbitrary unit like a census block, you can introduce bias into the mean of that covariate. So that means, again, if you have coarse geographic units and you're aggregating all your X covariates up, it can be hard to distinguish between, is there no difference at the border because the design worked, or if there is a difference, is it because the design failed, or is it the fact that these coarse units just have bias built into them because you've aggregated them? So that's another challenge in terms of the falsification test. And in general, all the problems I've talked about so far about the sorting and in particular, is that what tends to be the case here is that geographic designs have a less optimal treatment assignment rule than your standard two-dimensional RD. And what I mean by that is that what typically happens is that policymakers do not go out and draw a circle or some square into a space and say, we're going to treat those people. What they do instead is they map onto existing geographies like counties, right? That is, the treatment is assigned using existing borders. Counties being a common one, but city limits, lots of different things. What that means, however, is that given that that border has existed for some length of time, is that people may have been sorting around that border for all sorts of reasons, school districts, taxes, lots of things you can imagine, right? So that when you have, so there's some sort of discontinuity, some sort of difference between people. And the other thing is the geographic borders, they're easy to find, right? People tend to know exactly whether they live in Illinois or Wisconsin or not. And if you don't know, you'll find out as soon as you go to get a driver's license. For those very reasons, what happens is there tends to have been we think, in most cases, a lot of sorting that's happened before the treatment ever gets assigned. That's quite different than your classic RD, where what happens is the assignment rule is set, and then you need to enforce the assignment rule. Here, what you could do is something similar like that is if you went out and just drew a random circle in geography, that would probably be a much better geographic RD, and that it would be more likely to split people as if randomly with respect to geography. The problem is it's pretty rare for that to happen in most social science settings. One question to ask then is, if given that if you have an RD design, geographic RD design, and you find that there's still differences at the border, do you discard them? Right, in the RD literature, there's sort of an argument that if your RD design doesn't validate, right, if you don't pass these falsification tests, it's not a valid RD design anymore. What we argue is you should sort of treat this as a quasi-experimental device. And the reason we say that is, to my mind, is if we find that geography is making people more similar, right? That if you have a series of baseline covariates and you're comparing people just as a function of geography and they're becoming more similar, that's telling you that geography is doing something in terms of comparability. However, if you don't make it all the way there, that people are actually comparable, it seems a shame to sort of throw away the leverage geography is giving you. So what we have argued to do, so one thing you can do, I'll show you, talk about this, you can look at placebo test or sensitivity analyses. In particular, what we talk about is essentially we're going to call this a quasi-geographic experiment, where we're going to control for whatever x's we have, and we're going to assume that within some area, some narrow area around the border, once we control for x's, right, essentially then it's as if random that you happen to live on one side or the other. So again, this is a bit more like your classic observation study where we're having to depend on, right, conditioning on the right set of covariates, right? But the other thing that actually can happen here that is clearly not going to be an issue in any other kind of, in your classic two-dimensional RD, is the possibility of interference. So with these geographic designs, right, spatial proximity is the basis for identification. What I mean by that is we say our effect is identified if we think things are as if random. We're assuming here that if I get close to the border, if I get people who are close to each other, right, that they're going to be similar. What that means, however, right, is that the spatial proximity may lead to interference. Because these people live or work near each other, what's to stop them from the treated units giving some of their treatment to the people who live just over the border in the controls, right? Here, the possibility of interference tends to vary quite a bit. In the chip example, it's kind of hard to imagine how that's the case, right? You have to be eligible. There's no real way for me to give my copay to the people who live in Illinois. The medium market one is an interesting one, right? If there are a lot of ads just on one side of the border, are there any way for them to be exposed if you live on the other side? In the time of aerial TV, there was probably many instances for interference. Now that we have cable, it may be less. One example, however, where I've seen clear indications that this would be a possibility is they were looking at it was a geographic RD looking at the effect of mosquito prevention treatments. That is, they were spraying for mosquitoes, they were releasing sterile mosquitoes, right? And they're looking at that they were doing this by regions in Peru and looking at people who live near the border, right? It's very easy to imagine, right, that in particular, that these sterile mosquitoes would then spread across the border. And then thus the people who are in the control area would thus get some of the treatment, right? There's things you can do about this. Essentially, you can remove people who are super close, but that can be problematic in terms of dropping data, which could be sparse already. But with these designs, unlike your classic two-dimensional RD, you sort of always have to worry about some possibility of interference, right? The other thing is the effects are what we often call extra local. So in an RD design, the effect is local, right? Because it only really applies to the people who are just above and just below, right? You got some window where people look similar, but it's clearly not the effect for everybody. And in that sense, right, this is not the effect of CHIP for Wisconsin versus Illinois, right? In the classic, if you're using a geographic RD, right, depending on where you draw your little limit here in terms of where you think people are comparable, right, it's the effect of the CHIP the CHIP copays for people who happen to live here versus people who happen to live here, and the design can't tell you anything about if the people who live here are different, what the treatment effect might be for them. However, the other thing is, right, is there's often lots of sparsity here in this data. There's some people here, there's some people here, and there's some people here. And strictly speaking, in terms of the data we had, there's no one here. So the effects become more local in the sense that you don't have the effect across all of this. You only get effects at where places where you tend to have data density. So again, if these people tend to be different than the few scattered people who are here, right, there's nothing really in your design that can tell you about what that treatment effect is for people, other people out along the border, right? The other thing is tends to be the case is that spatial heterogeneity tends to be of greater interest. It's not clear to me whether we care that much different, whether the treatment effect might vary here, or it might be different for these people versus these people. But in this design, right, I might have reason to think about why the treatment effect could be quite a bit different here versus over here, right? This is part of the Chicagoland area. This is sort of a different, more different kind of Midwest city. So I might have reason to think this treatment effect is more is different in an interesting way than this one. Right. So briefly, I'll sort of run through the application, the analysis that we did to go back through some of these ideas, right? And I said the study is, did these copays reduce healthcare utilization? So the data comes from the Medicaid analytics extract. There are some covariates, right? They're not a lot. We have sex, age, and the main thing is we have past medical conditions. And the outcomes here are just the things that were covered under the copays, ER visits, hospitalization. And again, for privacy reasons, the Medicaid only gives you people's zip code. It will not, they have their address, but they will not give it to you, right? So essentially we've got this issue here where we're gonna have to, for these geographically, all of these covariates have to be aggregated up to this. And there may be some sort of bias as we aggregate up to the zip code, but we have no idea. Because unless you have the actual geographic spatial data, you don't know. So one thing that we often do in this instance is we buy property sales data. So here we purchased data about all the homes purchased along the border. The nice thing about that is you get an address, so that data is geospatially located, so you can get around this aggregation problem. And we essentially, the first thing you do is this falsification test. We do a balance analysis of the covariates to get an idea of how similar are people, right, at the border. Then later on, I'll show you they're not that simple. So we're going to do some geographic sort of matching that we came up with to control the covariates. And then we're going to use past outcomes as placebo test. Strictly speaking, if these people are truly comparable, what we should find is before the copays went into effect, right, we should find that if they're really similar, then their past healthcare utilization should also be similar, right? And then we can also use well-child visits as another placebo outcome because there was no copay added to that. So, right, so we should find no treatment effect on the well-child visits as well. And we're going to do this with, as I said, with this geographically matched data. So the other thing I want to talk about here is I'm going to refer to area 1 and area 2. So this is, there was not enough data in this area. So we did one analysis for these two set of counties, and we're going to call that area 1. And then we're going to do another analysis for these set of counties over here. And I'm going to call that area 3. We called this area 2, but again, there was not enough data density to really do anything. We had a little bit in terms of price data. So here I do have it in terms of house prices, but there wasn't enough Medicare data. So this gives you a little idea of the sort of what happens. So this is a county comparison. If you compare the house prices of Lake County versus Kenosha County, you find that houses are more expensive in Wisconsin. They're about $150,000 more expensive in Wisconsin. That's a fairly substantial difference. If you look at the border zip codes, that does go down a lot. That if you just look at the border zip codes, but if you actually match up houses that are close to each other along the border, again, the effect goes way up. And there's houses in Wisconsin tend to be about $100,000 more expensive, right? This is the problem I'm talking about. Is what we'd like to see is that these houses are super similar to each other in terms of price. But what we're seeing here is that the houses in Wisconsin are more expensive, and thus people could differ. We see this exact same issue here. It goes in the other direction, but there's about a $30,000 difference in this area. Here, things work a bit better. This is in the Beloit area. Houses are a bit cheaper in Wisconsin, but once as you get closer, you look at the border zip codes, and then people who are the houses that are just close, there's only a difference of about $2,800. That's not significant. You could argue about whether $2,800 is enough for people to be different or not. The flip side is also, of course, is our data density is actually fairly low here, though those are house prices, not the number of people who are in Medicaid or CHIP. So this is a table 1. The other thing that we see in particular that really jumps out is the part of Illinois is substantially more Hispanic, right? It's about 51% Hispanic relative to 22% Hispanic. We did some matching, and even after matching, the difference is just too large to take that out. That is, the treated area in Wisconsin is substantially different racial or ethnic makeup. We see the exact same issue. It's not as bad in area 3, but it's about 19% Hispanic in Wisconsin. The flip side here, the Hispanics tend to live in Wisconsin. So it's about 19% Hispanic on one side versus 7% on the other. And even with matching, we can make them smaller, but they're still fairly substantial. So the first thing we did is look at those placebo outcomes, right? No, there should really, strictly speaking, be no differences. This is a test looking at effects of being in the two states before there was any copays, and right, it's rather unfortunate, but there's differences, right? People in Wisconsin use well child visits at much lower rates. They use more outpatient medications, right? So it's, again, more and more evidence that these two places are just different in a number of different ways. It works a bit better here. The p-values are all large. The difference, however, is even some of those p-values, like if you look at ER visits, right, there are way more ER visits in Wisconsin than were in Illinois. That's marginally, that's just under 0.05, but even for these others, right, some of these are actually fairly substantial. It's about 35% versus 50% here. So if you do an overall analysis of table 1, right, we find, again, like before, there are just large differences, and it's hard to say that there's really anything going on. If you look at this pattern, so this is area 3, the area which we sort of believe the most in. There is one evidence that acute visits decline some a bit, but some of these others actually go up slightly. So again, very little evidence of any particular effect. So in theory, geographic treatment assignment creates no new difficulties. That is, strictly speaking, if you have a geographic treatment, it is, in theory, just a two-dimensional RD that can be analyzed. Like, there's a small literature on two-dimensional RDs, but there's a literature out there, and there's sort of nothing to stop you from plugging this into that sort of machinery. However, as I've pointed out, complications abound. These can be clean. We have a few small examples where they work pretty well, but in general, there's just a lot more going on. And in particular, as I mentioned, the two biggies are the fact that these borders are being, the treatment border is usually being assigned to something that exists, and people have been sorting around it for a while. And thus you just tend to get, even though they live close to each other and are different from each other, there are clear differences. I think it remains a promising identification strategy, but it's just a bit more difficult to use, and there's going to be more headaches. It's just not quite as clean as your classic RD. And that's the presentation.
Oh, sorry, I forgot I pulled down the thing. All right, thank you, Luke, for that presentation. At this point, Luke Keele is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And while we're waiting to hear questions from the audience, I'll ask a few that I came up with. Sure. So I think you did a really good job of addressing all of the sort of things I was thinking of as you were giving your talk, like, oh, what about this, what about that, and you thought of them. And so that raises, I assume this is the first question you always get when you give this talk, which is, why don't I just use, like, pool all the data from everywhere, not just near the border, and then try to fix all these problems using the standard approaches of control variables, fixed effects, maybe some sort of diff and diff thing, and I still have all the same problems, but at least I have a lot more data, right? What's the if these problems like sorting are going to exist near the boundary and they're going to create some sort of confounding problem, why don't I just address it in a bigger data set where I already have confounding problems? You know, there's sort of nothing new there, and at least I have more data.
So there are a couple of reasons. One is if you see in particular, so the first case, let's say you do see that you do find that while the people near the border are not identical, they're getting more similar, right? Mm-hmm. That is, like you saw in Milwaukee, they're getting more similar. So that seems to be saying that geography is removing some bias on its own, right? Mm-hmm. So there's a result, actually, a fairly old result by Cochrane that says in an observational study, if you have a fixed bias, because you've got some omitted variable bias, mm-hmm. you add data, the magnitude of that bias grows. Right? In a randomized experiment, we know there's no bias, so if you add more data, no big deal. Everything's heading in asymptopia, it's all heading to the right spot. Mm-hmm. The problem being in an observational world is if you add more data and you've got this fixed bias, you may be heading off in some other direction. Mm-hmm. So my general thing is, I'm not saying don't look at the other observational study, but if you have, but the general implication of Cochrane's argument is if in a more focused comparison, you think there's less bias, that there are reasons to use less data relative to more data. So now, if geography is doing nothing, if when you look at the house prices or whatever, and there's no change as you get closer, then you can abandon it because it's not doing anything at all. But if, however, in the Milwaukee one, and we have one in Ohio, where it's clear that when you get to this one little area, they have these people who live in the same school district, they're really similar. There are, I think, reasons to look at that area where you think there's less bias, even though you maybe have less data. Mm-hmm. Again, it's going to depend on if you think the observables are moving such that you think the geography is doing something about the bias.
Do you think that there's a question from the audience, so I'm going to follow up on my own question with just a short thing. How much do you think people are actually choosing their location based on the treatment? Meaning, like, in your case, you're talking about health insurance programs. Do you think people actually choose to live on one side of the board or the other specifically because of the treatment, which might then create some sort of endogeneity or simultaneity?
Probably not in this case. But if the reasons they sorted are all correlated, right? If the lower income people decide to live in, let's say it's cheaper to live in Wisconsin, so lower SES people decide to move there, and then you stick a copay on it, right?
Right.
Then it's essentially right. And you can go on a case by case basis. Maybe you think that's not the case, but often if there is a difference, in a lot of social science settings, it's hard to separate those differences. Mm-hmm. Especially if you're looking at house price and the houses are way cheaper or more expensive. And in most social science settings, SES has some relationship. Mm-hmm. So, yeah.
Well, we have a question from the audience, so I'm gonna ask that. Thomas B. Asks, as you noted, zip codes are pretty crude since the latitudes and longitudes are based on the centroid for the zip code. Why not use Census Bureau data and take the analysis down to the census tract level?
So it'll depend. Ideally, you would do that. Ideally, you would actually go as far down as you can. As I said, in this setting, Medicaid will only give you zip codes. They will not give you any other geographic information about them. And it's not uncommon that in the CPS, you only get information about geographic units that have populations of 100,000 or more. So in the CPS is the current population survey. So there are oftentimes, right, for instances totally beyond your control where you may not be able to get down to the census tract or what block or whatever. Ideally you'd go down to the block. That's my memory serves, that's the smallest census unit. If you can get that information, great. But it's this geographic data is latitude and longitude is becoming more common, but it's still not all that common. And in many, many government administrative data sets, unless you go through special rules. So there was one, they were looking at the difference of house prices on school quality and analyze that data. They had to go to some special census center and do all the analysis in the census center.
I have a question about, so one thing I always think about when I think about RDDs is, I guess you would call it, this is a sort of an external validity concern. Because you're obviously the most important observations are the observations that are very near whatever the discontinuity is. And in some cases, those the people or the units that occupy that discontinuity might be unrepresentative of the larger population in ways that are important to the treatment effect, right? There's been a lot of recognition over the last 10 or 15 years that moderation is an important thing and that treatment heterogeneity is an important thing. I'm wondering if you think that sort of generic problem of RDDs, it gets better or worse when you're using a geographic boundary as the discontinuity.
I mean, in this point here, I would say essentially this depends on the data, but this one here, when I talked about extra local effects, that is essentially worse, right? Because in the sense that here you've got external validity issues this way, but you may also get them this way because there's just not much data here. Mm-hmm. Right. So in some sense, that would never occur in a regular. I mean, I've never seen data from an RD with 2 test scores. So I don't know whether that issue shows up there or not. But I know with geography, there always tends to be empty areas or lesser areas. Mm-hmm. So in this case, right, what you can say is I can talk about it in a small town, I can talk about it in a suburb, but I can't tell you what the treatment effect is in a rural area. So in some sense, it's worse. Mm-hmm. Now, again, I can't, going in a priori, I can't tell you what your data density is. Right. The one we did in Milwaukee was not too bad. The only time we didn't have data density was like around the airport and a few other areas that were essentially just non-residential. So there you don't worry about it as much. But here it's different when the data just thins out for those other kinds of reasons. Mm-hmm.
Andres Sandoval says, thanks, Luke. The presentation is very clear. My question is, what happened with data that is clustered within borders? For instance, in your example, can we think that some people in the border on the border of the Beloit area might be similar with themselves, and same with the one in Chicago? It seems that you analyze these regions separately, but let's say you wanted to increase your sample size and pull them together. How do we go around this?
So this is a tricky question that happens in a lot of observational studies. So in randomized trials, it's well understood that if you have individual treatment assignment, you analyze it just like normal data. If you have cluster treatment assignment, let's say the classic example being schools, right? Or actually the classic example in political science is households. All the GOTV are typically treating households. You need to cluster the standard errors on the level at which the treatment was assigned. In that case, household. In observational studies, that gets a lot muddier in the sense that is what you have here, right? Is the treatment really just two counties? Is your N 1 and 2, right? Or is the actual sample size the density of however you write your bandwidth around there? Strictly speaking, there's a nice paper recently by Imben, Zabadi, Susan Ake, and somebody else, and they're right. You can cluster standard errors on many different dimensions, but in the causal analysis, the key thing is to cluster them on the level at which the treatment occurred. Again, this comes back to the idea of if I actually come through here and let's say I decide to draw a border right through here, I think it's pretty clear really what the treatment assignment is, right? That's an individual level treatment, and that I'm cutting people just like I would if I was to test scores. But it's a little less clear when you have, say, two existing counties and you decide to add a border or add a treatment to this border. In theory, you should perhaps cluster at the county level, right? But as is often the case in many observational studies, it's not, because we aren't controlling we aren't controlling the treatment assignment mechanism the way we are in RCT. It's kind of somewhat ambiguous about how you would correct those kind of errors.
Mm-hmm. Another question from the audience. The G word, gerrymandering. I feel like I can't have a political science talk lately without talking about gerrymandering. It's been a big issue with respect to the recent midterm elections. In your opinion, would an RDD framework be useful in attempting to understand the mechanisms around that?
Probably not. I mean, I think you could use it people have used it in the sense that if you want us to understand the effect of some aspect of a congressional district, like the race of you could imagine it being used there, like the race of the candidate. But in general, to me, that's a very different sort of, depends on what you mean by the effect of gerrymandering. It really depends on, but in general, we aren't typically looking at some individual treatment effect as a function of, I mean, we are in some cases, but typically the effect of gerrymandering has more to do with the state level representation, right? The delegation. And to me, that's a different question that's not really that useful for these kind of designs.
Yeah, it would seem like
I could be wrong, but that's my 2 cents.
I mean, my initial thought would be they're deliberately drawing the boundary with an outcome in mind. So trying to study that outcome would be a bad idea because they're literally attempting to modify the outcome with the line.
So you could argue back in the 80s, right? The GIS wasn't very good, so they were making lots of mistakes, and maybe it's better there.
Yeah.
But now they're pretty damn precise.
Yeah. Yeah, I was under the impression that some of us could actually get paid to do that kind of thing for parties. Yeah. So we're good at it now. All right, well we're a little early, but there are no more questions, and I don't think I should hold people here beyond the limit of the questions. So I'm going to thank Luke for being our presenter this week. I thought it was a great presentation. I want to mention that this presentation is going to be posted to our website and to YouTube, but that'll be on our website. I also want to advertise the next talk. On November 16th, we're going to host a talk by Kevin Munger, Princeton University and Penn State. His talk is going to be about mTurk samples and their suitability for analyzing treatment effects. Please see our website, www.methods-colloquium.com, to get more information about this talk. Thanks to everyone for being here. Luke, thanks for giving a talk today.
Yep, thank you.
And I hope to see everyone next time. Thanks.